Hi everyone. In this video, I want to talk about properties of relations. So as a reminder, a relation on a set X is just a collection of ordered pairs from X. That is, a relation is a subset of the cross product of the set X with itself. So for example, suppose X is the set ABCD and R is this relation right here, just this collection of tuples. Now, we can visualize this relation by drawing the elements of X, A, B, C, D, and then drawing an arrow from one element of X to another element of X when the pair BA is actually in the relation R. In such a situation, we write B is related to A. So this relation right here can be visualized as follows. We have A, B, C, D, and for example, we see that there's an arrow going from C to D because the pair CD is in the relation R. In such a situation, we write C is related to D. So these facts right here describe the relation. This is the relation. It's a set of ordered pairs, and this is a way of visualizing the relation. All right, so our first property is reflexivity. Now, what reflexivity says is that every element of X is related to itself. So for all X in X, X can see itself. What that means is that when we draw the graph, we're going to see these reflexive arrows, these arrows that leave a point and point back to itself. So reflexivity says for all X, X can see itself. Now, a generalization of this idea is completeness. What completeness says is that if you give me any 2 points, X and Y, so these are two arbitrary elements of X, and of course X could actually be equal to Y, but we just say, suppose that we have two arbitrary elements of X. Either it's going to be the case that X can see Y, or it's going to be the case that Y can see X, or perhaps it's the case that both of them actually hold. X can see Y and Y can actually see X. So for example, suppose that we have this set ABCD again, and now I want to come up with a complete relation. So in order to do that, I have to look at each pair of elements. So we can start with A and compare it to B, C, and D. So E has to be related one way or the other to C, one way or the other to D, and one way or the other to B. And then we continue. We say, okay, well then B has to be related one way or the other to C and D. So here we see that B can see C. Of course, it could be that B can see D and D can see B. That's perfectly fine as well. And then finally, we have to compare C with D. So there has to be a relation one way or the other with C, between C and D. So this is an example of a complete relation. Although the astute readers or watchers will have noted that I've left out something. And that assumption is I left out a possibility, namely that X and Y actually are the same element. So when we write for all X, Y in X, it doesn't have to be the case that X and Y actually are different elements of X. We think of X and Y as variables ranging over elements in X, and X and Y could, in principle, take on the same value. If X and Y take on the same value, then this actually becomes X is related to X, since Y is equal to X, or X is equal to X, since Y is related to X. In that case, completeness implies reflexivity. So given this definition of completeness, this is what a complete relation will look like. Of course, there are other possible complete relations on this set X, but this is one example. Now note, as stated, completeness implies reflexivity, meaning that this definition of completeness logically implies that the relation is reflexive, just because X and Y could be referring to the same element. Sometimes we want to be able to impose completeness without requiring reflexivity. In order to do that, we have to modify the definition of completeness to say for all X and Y, if X and Y are distinct. So we only care about requiring there to be a relationship between X and Y if X and Y actually are distinct elements. All right, so that's reflexivity and completeness. The next property is transitivity. What transitivity says, if you give me objects x, y, and z, suppose you have x, and here you have y, and here you have z, and you know that x can see y, so there's an arrow from x to y, x is related to y, and y is related to z, so y can also see z. So there's two steps that take you from x to z. X can see y, and then y can see z. Then it must be the case that x can see z in just one step. So x must be related to z. So for example, consider the less than relation on numbers, say real numbers. So the less than relation says, suppose I have a number a, and I know that a is less than b. So if a is less than b, then a must occur to the left on the number line. And suppose I also know that b is less than c. So if b is less than c, then b must occur to the left of c on the number line. But if that's the case, then it must be that a is to the left of c. That is, a is less than c. So that's an example of a transitive relation, less than on the natural numbers. Here's a more abstract example of a transitive relation. Suppose we have the set a, b, c, and d. If there's edges, or there's a relation between a and b, so a can see b and b can see d, then transitivity says that a must see d. So there must be an edge from, or an arrow from a pointing to d. So there must be a relationship. So this says if a is related to b and b is related to d, then it must be the case that a is related to d. Now, if there was an edge between c and d, so there's a c is related to d, so this means c is related to d. This, in addition to these other relationships here, transitivity doesn't require us to add any extra arrows. However, if it was the case that d is related to c, so d is pointing to c, then transitivity is going to require us to add some arrows. And sometimes, and here's something you have to watch out for, sometimes it's going to require that you add two arrows. So for example, note that a can see d, a is pointing to d, and d is pointing to c. Note also that b is pointing to d and d is pointing to c. So this tells me that there are going to be two arrows that need to be added in order to satisfy transitivity. So we need to add a has to be related to c and b has to also be related to c. So this is an example of a transitive relation. Now, one thing I want to point out, what happens when a relation is not transitive? Suppose that you have a relation and somebody tells you that it's not transitive. Well, what that means is that there has to be objects, a, b, and c, such that a is related to b, so a is related to b is related to c, b is related to c, but it's not the case that a is related to c, so a is not related to c. The transitivity would require a to be related to c, but I'm supposing that this relation is not transitive. Now, what could happen? Well, it could be that a and c just aren't related. There's no, a is not related to c and c is not related to a. Now note, this would violate completeness. So this relation that I have drawn right here is not complete. So if I do require completeness, I do want the relation to be complete, then there has to be a relationship. There has to be some relationship between a and c. And if I'm assuming that my relation is not transitive, what does that mean? That means that c must actually be related to a. Now, the situation we have here, we've created a cycle. A is related to b is related to c, and c is related to a. Cycles are an important topic in rational choice theory because if there's a cycle in say, a preference ordering, then it's unclear what the best element is. You can't really point because here's A, there's always another element that's better than the element you're pointing to. So a cycle in a relation R is just a set of distinct elements from X such that X1 is related to X2, X2 is related to X3, X3 is related to X4, and so on. This is related to Xn. and then xn must be related to itself. One thing I want to point out is that when you say that a relation has a cycle, so R is cyclic, that just means there are some elements from X that form a cycle. It doesn't mean that the cycle has to involve all the elements of X. For example, we could have a relation that looks like this. A is related to B is related to C is related to D is related to B, and maybe A is related to each of B, C, and D. So notice here, there's a cycle involving B, C, and D, but not involving A. So saying that a relation has a cycle just means that there's some cycle in the relation. There's some set of elements that form a cycle. And then we say that R is acyclic if it doesn't contain any cycles. Okay, couple final properties, and they kind of all go together. Symmetry, anti-symmetry, and asymmetry. So what symmetry says is that if X is related to Y, so if X can see Y, then it must be the case that Y can see X. So if X is related to Y, then Y must be related to X. Anti-symmetry says that if you know that X is related to Y and Y is related to X, well, then it must be the case that X actually equals Y. So for example, consider the less than or equals relation on numbers. If the number A is less than or equal to B, and the number B is less than or equal to A, well, the only way that that can possibly happen is that if A is actually equal to B, if the numbers are the same. And then finally, we have a stronger property, which is asymmetry. So a relation is asymmetric if, for all X and Y, if X is related to Y, then it can't be the case that Y is related to X. So if X is related to Y, then it cannot be the case, so this relation here can't be there, that Y is related to X. So an example of an asymmetric relation is the less than relation, the strict less than relation. If A is strictly smaller than B, then it can't be the case that B is strictly smaller than A. So these are some properties of relations. There's many, many more properties that mathematicians and economists and philosophers have discussed, but these are some of the most important properties, and we will discuss these in more detail throughout the semester.